In this video, let's look at a few more questions on complex logic gates. So consider the circuit given in the figure. Give the Boolean function for the output y. Design a pull-down network for the gate. Size the gate such that the worst case pull-up and pull-down resistances are equal to half of that of the smallest inverter in this technology, which is sized 3-1. Right? Find the delay for the transition from 010100 to 011100. If the output doesn't transition completely for this change, indicate the delay for the output to reach steady state voltage. You can assume that there's no cap reduction at the shared source drain. Right? So now let's look at the gate a bit. Right? So the gate, if you see here, easiest way to do this, to do the pull down network, would be to do the dual of this and then write the function. So you can do either way. Either you work out how the PMOS pull up works, or you first create the dual and then write the function of that. So we know that the output node charges up to 1 when at least one of the PMOS in these pairs is turned on, right? And so therefore I can write my Y as a product of A bar plus B bar, C bar plus D bar, or E bar plus F bar. Or in other words, if I combine that, it's basically Y is AB plus CD plus EF, the whole under the bar, right? And so the pull down network, if I had to do, basically it consists of 3 paths. Each path consists of 2 transistors each. So this, my pull down network becomes AB, CD, and EF. So Y goes to 0 if either one of these pairs goes to a value of 1. Now we're asked to now design this gate or size up this gate such that its resistance is half of the smallest inverter. So the smallest inverter is sized 3-1. Right? Now if I want to, so the smallest inverter is sized 3-1. And if I want to design an inverter which has half its resistance, then I need to blow up its size. And so basically I need to size the inverter size is 6-2. So now I need to design this gate in such a way that its pull up and pull down resistances are matched to 6-2 and not 3-1. Right? So let's draw the complex gate again and let's look at the pull down network. So in the pull down network, the worst case pull down path consists of 2 NMOSs in parallel and in series. And because the 2 NMOSs have to be in series, the size of each NMOS has to be double of what it is in this gate. Right? And so it would be 4 and 4. So this ensures that the worst case pull down resistance is going to be similar to this larger inverter. Similarly, if I look at the worst case pull up path, the worst case pull up path always consists of 3 PMOS transistors in series. And so therefore I'm going to size up each PMOS to be 3 times that of this PMOS so that I get the same resistance, and therefore my PMOS is sized up to 18. Right? And so this should be the final sizing of this gate. And this is important because that's going to determine what your various diffusion capacitances are in this gate. Now let's look at the transition. You're asked to find the transition delay when ABCDEF go from 010100 to 011110. Now the function is given by AB plus CD plus EF, the whole under the bar. Right? So when the inputs are 010100, my output is a 1. And when my inputs transition to this set of inputs, my output goes to 0. So basically I'm asked to find the falling transition delay at the output node. Now there are 2 inputs transitioning, basically the C going from 0 to 1 and E going from 0 to 1 simultaneously. Right? And so in this case, nothing is given. To keep our life simple, we assume both of them transition at the same instant and transition instantaneously. Now let's go and look at this gate. So because of the fact, now again, this is the gate drawn for illustrating purposes. Now let's look at this intermediate node. So we know that when you're going to do the transition delay, we are worried about where these intermediate nodes are, right? Are they close to 0 or not? So for example, if you look at A is always at 0. Now when A is always at 0 means that this node, which is sitting here, is always at VDD, right? And remember, we are looking at a falling transition, right? Now, and similarly, if you now come here and see, now obviously I've chosen AB in this way that B and D are the closer to ground. So when B was 1, remember B is always 1. So when B is 1, this node is going to be at 0. Similarly, D is 1, this node is going to be at 0, right? And so when C and E are transitioning, right? C is transitioning, it makes no difference because it has to transition only here. The question happens when E is transitioning, right? So when C goes from 0 to 1 is what's going to happen to this delay. So if I were to draw the Elmore circuit, this is my output node, right? My my C transistor is the one that's actually going to be pulling my output node to 0, right? And so if I look at that, what I have is my output node R by 4 because both the C and D are sized 4. So this is R by 4 and that's R by 4, right? And then I have 48C connected to this output node. Now there is no capacitance connected at this node because the capacitance between C and D has already been discharged. Because D was already 1, this capacitance has already been discharged, already at 0. So I don't need to worry about this capacitance. The capacitance I need to worry about is this huge capacitance at the output node, which I need to discharge. Furthermore, remember when I do E 0 to 1, right? F is 0. So my F sees this path. So this node is also a VD. That also needs to be pulled, right? So in fact, what you're going to see is that this node is loading up the circuit. So this node is 72C connected via an R by 12, which is this transistor F to output node. Now the delay I want to find is from the ground to Y, right? Not the delay obviously to this node is going to be longer. But I want to find the delay from 0 to Y. But this node is going to impact that delay. So what you see therefore is your delay is going to be given by R by 2 into 48 plus the same R by 2 into 72. So this 72C sitting here is going to drive a longer delay at Y. And so what you see is your tau is roughly 60 RC. Right? And that's coming primarily because of this large capacitance sitting here. Otherwise, it would have been 24C. Because of this big 72C sitting here, that's the one which is causing a large delay at the output node. Let's look at a generic logic family question. In a particular logic family, the standard inverter, when loaded with a similar circuit, so which is loaded with the same inverter, has a propagation delay of 0.9. Now, if the current available to charge the load capacitance is 60% as that available to discharge, find tau PHL and tau PLH. So what we are saying is that the charging current or the PMOS is only is 60% as effective as the NMOS. That is, the drive strength of the PMOS is only 60% that of the NMOS, and you're asked to find the rising and falling delays. Now, if an external load of 0.5 puff is connected to the inverter output, its propagation delay increases by 40%. What is the normal combined capacitance of the inverter output and the input? So when I add half a puff in addition to the output node of the inverter, I see that my delay goes up by 40%. So that gives me an idea as to what the magnitude of the capacitance is. And if I remove, so without the additional puff load connected, if I load inverter is also removed, then the delay dropped to 40% of its value. You're asked to find the parasitic cap in the inverter and the gate cap of the inverter. So let's do the first question. So you're given that the propagation delay of the inverter is 0.9, and you said that the charging current is only 60% the discharging current. And so if you think about it, the load capacitance is the same. So therefore, if the charging current is only 60% the discharging current, it's going to take longer to charge the capacitor than it is going to take to discharge. So what I can therefore say is tau p low to h, right, by tau p h to low is going to be 1 by 0.6, right? It's going to take longer to charge up the output node. And so I also know that the propagation delay is the sum of the inversion, falling and the rising delays. So I have two equations and two unknowns, basically the rising and the falling delay. So I solve for them and basically I get the rising and falling delays to be 1.125 and 0.675. So the falling delay is faster because the NMOS is faster. The rising delay is slower because it's the PMOS is only able to supply 60% of the NMOS current. Now let's assume for the second question we're asked to find the capacitance at the output node. So let's assume that the total capacitance at the output node is some C total. Now what I was told, I was told that I added another capacitance to this node. So when I added a capacitance to this node, the net C load changed, but my driving capability of the transistors did not change. And so I saw that when I added this capacitance of 0.5 puff, my delay went up by 40%. So or in other words, this total capacitance works out to be 40% more than what it was. So 0.5 is actually adding 40% more to this total. And so if I work out the math, that tells me that the total capacitance I have today in the inverter is 1.25 puff, right? Because then 0.5 puff is 40% of this total capacitance. Now when I remove the load inverter and only the parasitic cap, that is the self-loading of the inverter stays, I see my delay drops to 40%. That is, my parasitic capacitance is only 40% of my total capacitance, right? So therefore that gives me a value of what my parasitic capacitance component is of the total capacitance. And so therefore, given the total capacitance, I can now find my parasitic capacitance. That is again puff, 0.5 puff, which tells me that my total gate capacitance is total capacitance minus the parasitic capacitance, which is 0.75 puff. So it's a very simple question related to understanding what the net capacitances are and the fact that the transistors are not changing. So if you're playing with the loads on these inverter, you can estimate the capacitances on the inverter. Now let's look at a very standard problem you'd see in almost any logical effort based sizing question. So I think I put this in as an illustrative example. A lot of sizing questions can be essentially boiled down to a problem, something of this sort. So a fairly important question to keep in mind and gives you a sampling of how most people like to question in this field. So consider the following circuit. The input NAND has an input capacitance of 10 units. The output capacitance is 90 units, where 5 units denotes the gate capacitance of the smallest inverter in the technology, sized 3.2. Right? So this path basically consists of this 4-input NAND feeding into these two input NORs, and each 2-input NOR is feeding into 4 2-input NANDs. So you're asked to calculate the path effort in the critical path of the circuit, size the critical path for minimum delay, show the transistor level sizing of the gates. Can this design be improved for smaller delay? If so, suggest the modification and resize. What is the percentage improvement in delay you're able to achieve? Assume approximating the circuit area to be the total gate area. What is the estimated percentage increase in the circuit area you're getting? So let's first start, and typically in problems like this, it's a good idea to first figure out the critical path and then figure out all the logical efforts, parasitic delays, branching efforts, etc. So the smallest inverter in this technology is a 3.2 inverter, that's PMOS size 3 and NMOS size 2 with an input capacitance of 5. If we look at the 4-input NAND, which is the first stage of this path, given that I want to size it in similar fashion, you're going to have 4 PMOSs connected in parallel. So the PMOS size continues to remain 3. However, you have a 4 tall stack of NMOS in the pull down path. And so I'm going to size up the NMOSs to be 4 times that of the smallest inverter. Right? So the NMOS is sized up to 8 and the PMOS remains at 3. So in this case, therefore, if I look at the logical effort of this gate, at every input it's the same. It's going to be given by the total capacitance. Given the fact that both the resistances are the same, logical effort is the total capacitance in this node, which is 8 plus 3, 11, compared to that of the inverter, which is 5. So 11 by 5 is the logical effort of this NAND. And if I just lump it to the parasitic delay, the parasitic delay of this NAND is going to be the total diffusion capacitance here compared to diffusion capacitance of this inverter. The diffusion capacitance in this inverter, again, normally we assume gate and diffusion to be equal. So this is going to be phi C here. And if you look at the total capacitance here, it's going to be 3 plus 3 plus 3 plus 3. So 4 times 3 plus the diffusion capacitance of this topmost NMOS gate. So it is 3 into 4 plus 8 by 5, which works out to 4. So the parasitic delay in this 4 input NAND is going to be roughly 4 times longer than the inverter. The other gate which is being used in this data path is a 2 input NOR. Again, sizing the 2 input NOR, the 2 input NOR consists of 2 PMOSs in the series and 2 NMOS pull downs. So the NMOS size remains the same at 2. The PMOS, because it's a 2 tall stack, I size it up as twice. So the PMOS is sized as 6 and 6. So therefore the logical effort here is going to be 6 plus 2 compared to 5. So 8 by 5. So, and if you look at the parasitic delay is going to be 6 plus 2 plus 2. So 10 divided by 5 or 2. So this gate has a parasitic delay which is twice as long as the inverter. And lastly, we look at the other gate in this data path, which is the 2 input NAND. The 2 input NAND, using the same logic as the 4 input, you don't change the size of the PMOS. The NMOS in this case only doubles because it's only a 2 tall stack of NMOS. So it's 4 and 4, which gives you a logical effort of 4 plus 3, 7 by 5, and a parasitic delay of 6 plus 4, which is 10 divided by 2, or by 5, which is 2. Right? So both 2 input NOR and NAND have delays roughly twice, have parasitic delays roughly twice that of the inverter. Now, like all data path designs, now we go in and do the path effort calculation. So this is the data path we're trying to design, right? So all stages typically write it down as a stage level. So you have 3 stages: first stage, second stage, and third stage. For each stage, note down its logical effort, parasitic delay, and the branching effort if there is. Right now, in this case, you see that at the output of the stage 1, it feeds into 2 stages, 2 inputs in stage 2. Therefore, the branching effort of this stage is going to be 2. Right? Similarly, if you look at the output of the NOR 2, the output of the NOR 2 goes into the inputs of 4 NAND 2s. And so the branching effort of this stage is essentially going to be 4. Right? So now I now have all the logical efforts and the branching efforts. So I can talk about the path logical effort, which is the product of all logical efforts. In our case, we just calculated 11 by 5, 8 by 5, 7.5, 7 by 5, which works out to 4.9. The path electrical effort is unchanged. It remains as the output divided by inputs, so 90 divided by 10, which is 9. So that's the electrical effort of the path. The branching effort here, because now obviously here, remember that this NAND 4 has to do twice more effort, because instead of driving this gate, it needs to also drive this gate, right? And so therefore that impacts the delay. So the branching effort is the product of all the branching efforts of the stages, so 8. And so if I look at the total effort in the path, it's going to be GBH, which is 354.816. So that's the total effort in the path. Number of stages I have is 3. So now that I know the total effort and the number of stages, I can optimize the effort per stage for minimum delay as the nth root of the path effort, which is cube root of 354, which is 7.08. So 7.08 should be the minimum delay through, or should be the delay through every stage. If I size them up in such a way, then I'm going to get, without doing anything, I'm going to get the minimum delay for this data path. So how do I do the sizing for that? Right? So if I want to size it, again, remember the cap at the input of stage 3, that is for the 2 input NANDs, is Y, and the stage 2, which is the 2 input NOR, is X. Now again, always we start calculating from the last stage. So if you look at stage 3, which is the last NAND 2 stage, I have 7 by 5, which is the logical effort of that NAND 2, times 90 divided by Y. Remember, 90 is the output capacitance at the output node. Y is the input capacitance of every NAND 2. So this should be the delay, or F cap, which is 7.08, which basically gives you the value of Y to be 17.8. And once you know the value of Y and you know the size of the NAND to gate. You know the NAND to gates have to be sized with the PMOS being 3 and the NMOS being 4. So the ratio of 3 is to 4. That essentially gives you your PMOS size to be 3 by 7th of the 17.8, which is 10, and NMOS is 4 by 7th of the 7.8, which is 7.6. So these are the sizes of the PMOS and the NMOS gates. Now we come down to stage 2, which is the NOR 2 stage. In the NOR 2 stage, what happens is you have logical effort 8 by 5. But here the output capacitance of the NOR 2 is made up of 4, right? Because you have a branching there. So 4y times by x is f cap. And that essentially gives your x to be 16. And then you know the ratios of P and N in this case, which gives you one out of 6 by 8 of the 16, which is 12, is the size of the P. Size of the N is 4. So that's the sizing you need to do for the second stage. For the first stage, sizing is easy because you know the input capacitance is 10 and you know the ratios of the P and N. So the ratios roughly work out to 7 is the size of the P and the size of the N is 2.7. And if I want to find the total path delay, now this is the path delay minimized for this path. It's going to be N times F cap plus P, which is 3 times 7.08 plus 8, which is 29.24. So if I don't do anything and all I do is just resize the gates, then the best delay I can get for this path is roughly 29.24 normalized delay units. And if I just calculate the area by summing up all the W's, it works out to 113. Right? Now, is this the most optimal? Is the question. And obviously, we know that given that your F cap is 7, we know that it's not optimal. Again, I'd recommend you go and look at the old lectures. You see that you can add inverters so that you get an optimized delay roughly when F cap is 4 or the FO4 delay. And so therefore we can add inverters to this technology. So let's first find what the optimal number of stages are. So if I want to ensure that every F cap is close to 4, then the number of stages I need to find are basically log to the base 4 of F, which works out to 4.24, right? So which means that I can either add n equal to 4 or n equal to 5, right? Normally we would add n equal to 4, but in this case I just wanted to do both to show you what the impact would be on the delay and the area. Now note one thing here is I've assumed that the logic is agnostic to the number of inverters that you add. Now typically remember that every time you add an inverter, you're basically inverting the output, right? And sometimes that may be acceptable, sometimes they may not be acceptable. So depending on the use condition, right, you might be in a specific condition where you can add either 2 inverters or 0 inverters, right? So if that happens, then you need to do this with a lot more care, because as you'll see, it's really a trade-off question as to how much are you willing to pay for that delay reduction. So if I were to think about purely from an n equal to 4, today right now n is 3, you have 3 stages. So if I want to add one more stage, I need to add an inverter at the end. So that would be one stage with an input capacitance of Z. And if I'm going to choose a 5-stage solution, then I add 2 inverters at the end, in which case let those input caps be Z and U. So now let's do this calculation simultaneously for n is equal to 4 and compare it to what it is for n is equal to 5. Now if I'm going to use n is equal to 4, my effective delay per stage works out to around 4.3. And if I use a 5-stage, then my effective delay per stage works out to around 3.24. So you see that by adding a stage, you see a substantial reduction in the per stage delay, but this has more number of stages. And so if you look at 4.3 times 4 and 5 times 3.24, the numbers are roughly equal. Now, fifth, when you look at, again, like always, start from the end. So when n equal to 5, you have 5th stage, which is not present in the 4. And so calculate the 5th stage delay. Logical effort of this is an inverter. So it's 1 times 90 by U is F cap, which gives your U to be 27.81, which works out, you know the ratios for the NMOS and PMOS in the inverter. This should be 3 and 2, sorry. So you see that the ratio is, the PMOS is 16 and the NMOS is 11. Now when I go to stage 4, that's when I get the first stage in the n equal to 4 and the second stage in n equal to 5. So n equal to 4, this is my first stage, and the first stage size of the p and n are roughly 12 and 8. Whereas in the fourth stage, which is the penultimate stage in the 5 stage network, that works out to size 5 and 3. So one thing I'd like to draw your attention is look at this. When you add inverters, this last stage absorbs a lot of the area from the output capacitance, right? And then you see subsequently you see a reduction in the amount of on the size of the transistors used. Now, if you come down to stage 3, which was the penultimate, which was the last stage before we added inverters, now you see in this case your sizes have come down drastically. Again, 7 by 5 into 20.73 by y is 4.34. So your P and N come out to 2.8 and 3.7, whereas in the other case it works out even smaller to 1.6 and 2.1. Right? And if I go to the NOR 2 stage prior to that, it's stage 2, and stage 2 works out to be 7.27 in this n equal to 4, and roughly 5 and 1.8 in this n equal to 5. And finally, if I go to the first stage is going to be equal in both cases because the input capacitance is set to 10, so they're equal to both. So now if I look at the delays, right, the delays here in this case is going to be n times f cap plus p. I've added one inverter, so the total parasitic delay goes from 8 to 9, 4 times 4.34, so this works out to 26.36 normalized units. In the 5 stage, it's 5 into 3.24, plus you add an additional because of the 2 inverters, so you get this as 26.18. So by adding one stage, I'm not getting a huge improvement in delay. So if you see the percentage reduction in delay, it's roughly 10% if I went by adding this one inverter. And by adding another inverter stage, my delay reduces only by an additional 0.5%. So there's not a lot of reduction in delay beyond this point. However, what happens is that this delay comes at a cost of roughly 30% increase in area because you're adding another stage. And what you see is that if you add 2 stages, that's a huge, almost a doubling of the area for really not a lot of change in the delay. And so this is where, engineering judgment comes in, right? Is this a high cost to pay for this delay? In most cases, it is. So your primary point would be to go to this kind of a solution where you eat the 34% area increase and live with this 10% reduction in delay. So again, let's look at another problem. Again, this is drawing on similar concepts of logical effort and path efforts. In order to implement an OR4 logic to drive a 6.8 femtofarad on-chip capacitance, we end up with 2 options. So either I implement the OR4 as a NOR4 with an inverter, or as a NOR tree. So I have 2 NOR2s and a NAND 2 connected to it. Assume, so in brackets you see this 1x. So NOR4 1x means that it's the smallest NOR4 gate. Inverter 5x means that it's an inverter whose size is 5 times that of the smallest inverter. So this indicates the reference to the size of the gate, right? So assume that the reference is a 2-1 sized inverter and the gate and diffusion capacitance per unit width is C is equal to 1.25 femtofarad per micron. Assume the size ratio of NAND 2 is in option B to make the 2 options achieve the same delay. Assume the minimum CMOS transistor width is WP plus WN is equal to 80 nanometers. The convention NOR to BX means the transistors in NOR to gate are sized B times larger than the smallest NOR to in the technology. Right? So let's look at this problem. So first thing is let's try and first figure out the inverter. So the inverter, we know gate cap and diff cap are given by 1.5 femtofarad per micron. Our total gate cap, our total gate width of the inverter is 80 nanometers, out of which WP and WN in ratio 2:1, right? So therefore WN is roughly 1/3 of this, WP is 2/3 of this. Now the input cap is just the sum of this WPs, right? So if I look at the input cap, it's going to be this 80 nanometers times 1.25 femtofarad per micron. So it's 0.1 femtofarad. So that is the input capacitance of the smallest inverter. Remember, we need to drive a capacitance of 6.8 femtofarads, right? And so if I look at 3C, it's that is, if I think about the capacitance of the NMOS gate of the smallest inverter, if I call that as C, then 3 times C is 0.1 femto, or the C is 0.1 by 3, so 1 by 30 femtofarad. So that tells me the gate capacitance or the diffusion capacitance of the smallest NMOS in this technology and smallest PMOS in this technology is 1 by 30 femtofarad. This becomes important because as we size it, then we know how to get the capacitances for all other transistors in this design. So what are the two designs? We're looking at first path, which is 4 input NOR followed by an inverter, or we're looking at this NOR tree, which consists of 2 NORs followed by a NAND. And you want to basically find the value of B such that these two delays are equal. So like always, let's do the logical effort tree first. So what are all the gates we have? We have a NOR4 gate, whose, if I were to size up the NOR4 gate, remember that the 2 input NOR, the smallest inverter here is a 2-1 technology. So for a NOR4, I have 4 PMOSs in series. So the PMOS has to be sized as 8. NMOS doesn't change in size. Logical effort is 9 by 3, which is 3. Parasitic delay is going to be 8 PMOSs contributing, 1 PMOS of size 8 contributing to 8, and 4 NMOSs each of size 1. So it's 8 plus 4 by 3 or 4. And the total input capacitance is going to be 9 times C, which is 9 by 30 or 0.3 femtofarad. If I look at the inverter is 2, 1, logical effort 1, parasitic delay 1 with an input cap of 0.1 femtofarad. The NOR2 gate again is going to size as 4-1 because it has a PMOS stack that is too tall, LE of 5 by 3, and a parasitic delay of 2 with an input cap of 5C, which is roughly 0.167 femtofarad. And the NAND2 similarly is going to be sized 2-2 because this is a 2-1 technology. Logical effort is 4 by 3, parasitic delay is again 2, and the input cap is 0.13 femtofarad, right? Now let's calculate the delays in these individual paths. So let's look at the first path, which is a 4 input NOR and a 5x inverter. So delay can be written as delay through the first stage plus the delay through the second stage. Delay through the first stage using the linear delay model is G1 H1 plus P1 plus G2 H2 plus P2. So we need to find, we know G1s, we know P1s, G2, P2. We just need to find H1 and H2. Now H1 is nothing but the electrical effort of the first gate, which is the total output capacitance, or rather input capacitance of the next stage by the input capacitance of the previous stage. Input capacitance is 5 times inverter, so 5 times 3C, divided by the input capacitance here 9C, so this is 5 by 3. So that's the electrical effort of the first stage. The electrical effort of the second stage, I have to derive a 6.8 femtofarad capacitor here. And my input capacitance is 5 times 3C. I know 3C is 3 by 30, and this is where this was important to calculate. So from this, I get the electrical effort of my second stage has to be 13.6. Now I know G's and P's, so I can quickly now do the D1. So my D1 is 3 times 5 by 3 plus 4, which is 9. D2 is 14.6. So this stage is the slower of the two. Also, you see, here I'm not doing any minimization, so the delays are not matched. The delay of this stage is smaller than the delay of this stage, and my total delay therefore works out to 23.6. Right? So this is the path delay of path A. Now let's look at path B. The critical path consists of one NOR2 gate and one NAND2 gate. So again, D can be written as G1 H1 plus G2 H2. Now the electrical effort of the first stage is nothing but B times 4. Remember the input of the NAND is 4C. So B times 4C divided by 2 times 5C, because this is size 2, which is 0.4 B. H2 is 6.8 femtofarad divided by B into 4C. Again, you know the value of C, so this works out to 51 by B. Right? So this is the value of H2. And so my total delay for the first stage is 0.67 times B plus 2. Delay of the second stage is 68 by B plus 2. And the delay, therefore, of this path is 0.667b plus 68 by b plus 4. Right? So you see an interesting thing here, right, which is known in the logical effort world. The size of this stage affects the previous and this delay, right? If I make this size larger, it makes the delay of the previous stage larger, but makes the delay of the current stage smaller. So I need to now find the value of b such that this path delay matches the other delay. So when I equate the two, I get a quadratic in b, which I can solve to get the value of b, which is roughly 4. So this tells me that my NAND2 that I'm going to use has to be roughly 4 times the size of the smallest NAND2 gate in this technology.